Tamamdır. So, in the previous lecture, we were mainly focusing on the matrix representation of linear transformations, right? So we said that if you are given a linear transformation such that y is equal to ax, and if you can represent this y vector with respect to some basis in your codomain, and if you represent this x vector with respect to some basis in your domain, there is a n by n matrix which relates those representations, okay? So if y is equal to, let's say, if y is equal to ax, you can find matrices such that y of c is equal to a matrix times x of b, okay? And we also said that, okay, you can write down a procedure for that such that you take each vector in B, the basis set in your domain, and transform them through the linear transformation A, and you get the resulting vectors in terms of the basis vectors in C. And we put those coefficients in the columns of our matrix. And when we are done with all of the basis sets in B, we are done with constructing our A matrix over here. And we have seen some examples over there. So these are the coefficients appear in the column of A matrix. Different examples as follows. And at a later stage, we said that, okay, so this A matrix is a function of the our choice on basis functions in the domain and codomain. And the question was, what happens if we change the basis in the domain or if we change the basis in the codomain, right? And we said that, okay, if you are changing the basis, then there's another matrix which is transforming one representation into another. Here it is the P matrix. And here there's another invertible matrix Q transforming one representation into another, into your new basis set over here. So, and if you, that is the Q matrix in this example. And then you can obtain the new matrix representation with respect to your new basis sets from the old matrix representation, which was respect to old basis sets. And the relationship was just simply the QAP, right? A bar was equal to QAP. And just seconds ago, I said that, okay, if C bar is equal to B bar and C is equal to B in a special case, then Q turns out to be P inverse here, because P converts B bar representation to B and Q inverts C representation to C bar. So Q is equal to P inverse in that special case. And in that special case, A bar can be simply written as P inverse AP. So do you have any questions up to here? If not, we will continue with our examples. Any questions? All right, so let's continue with our next example. So the next example states that consider the 90-degree counterclockwise rotation example and find P such that the representation of a vector with respect to B2 can be converted to B1 and verify that A2 is equal to P inverse AP. Okay, so first of all, let's go back to the example. And where was it?
36. sayfa hocam. Sonu.
So one second, it was over here, right? So we do have different basis set and we have 90 degrees rotation, right? And this 90 degrees rotation transformation can be represented by different A matrices. We said A1 if the basis sets are chosen to be B1 and B1 in domain and codomain, and A2 is the case when the basis sets are chosen B2 in the domain and B2 in our codomain again, okay? And we found these matrices 0, 1, 1, 0, 1, 2, minus 1, minus 1. So what are those? B1 is V1 and V2, B2 is V1 and V3, and these are V1, V2, V3. So maybe we can draw those guys down there. Okay, let's go back. So this was V1, this was V2, and this was V3, right? And B1 was V1, V2, and B2 was V1, V3, right? And A1 was for B1 to B1, and A2 was from B2 to B2. All right. So we can find A2 from A1 as well, right? According to our discussions over here. So if we are changing basis sets in the domain and so on, we can find the A2 from A1 as follows. So when we have a look at the first matrix over here, so in order to do that, if I'm changing the basis here, I should be able to find P matrix which converts the representation with respect to new basis to the old one. Okay, so let's write that one. So I need to find the representation with respect to my old basis as a P times my representation of a vector with respect to B2. Okay. And how do we do that matrix? Do you remember that? So in that one, we were writing uh, the vectors in our basis set here in terms of the basis vectors here. We were expressing them as a linear combination of the weighted basis set of here, B1, and we were writing down the coefficients, right? So if we continue that way, let's start with maybe I can, since we have done this many times, I can write the P matrix column by column, right? So what is the first vector in B2? That is equal to V1. And how can you express the V1 vector in terms of the basis vectors in B1, in terms of V1 and V2? It is 1 and 0, right? How about the second vector, V3 over here? How can we express V3 in terms of V1 and V2? So it was equal to V1 minus V2. So V1 here minus V2 here, then I get V3. So I will write down V1 times V1 and minus 1 was V2. Okay, so that will be simply equal to my P matrix. And all I need to do is that then, in order to find A2, it is simply equal to P inverse A1P. Okay, and if you compute P inverse here, and that is again 1, 1, 0, and minus 1. Okay. And then if I write down
Hocam
as...
pi maddesinden emin miyiz?
Evet, eminiz.
Tamam o zaman.
Siz çok emin değilsiniz galiba. Varsa bir
Evet.
konuşalım. Hangisinden?
V3.
Maybe we did a shortcut there, so I can be more explicit, right? So V1 is equal to 1 times V1 plus
Evet.
0 times V2, and V3 is equal to minus, sorry, 1 times V1 minus 1 times V2, right?
Ama V3'nin uzunluğu da 1 değil miydi?
Nope, it was square root of 2. Okay.
Okay.
So this is minus V2, and this guy was here like minus 1. Okay, and
Okay.
1. Good. Thank you. Maybe I can undo this so it is not. So let's save and delete. Okay. All right, and let's continue with the calculation. So it's going to be 1, 1, 0, minus 1. A1 was 0, minus 1, 1, and 0. And P is again 1, 1, 0, minus 1. And that will be equal to 1, 1, 0 minus 1, and that will be simply get the first row over here, 0 1, that will get the first row there, 1 1, and that will be the summation of two rows, right? There's 1 2, and that will be the minus of this guy, minus 1 minus 1. And as you see, that is the same as what we have found A2 by directly computing the transformation matrix from B2 to B2. Okay. And the good news is that sometimes if you just know this P matrix or the P inverse matrix, those Q matrix, etc., you don't have to know the linear transformation itself. You can work on the matrix presentation of the linear transformation directly. What I mean is that if you know the P matrix, you can find A2 from A1 directly without knowing the linear transformation itself. Okay, so that might be useful. Okay, so as I said in the previous lecture, we will consider the rank nullity theorem in this lecture, but let's talk about range and null spaces once again. So we'll start those discussions by our theorem over here. And here we are given a linear mapping A from V to W, V being the domain, W being the codomain. And the dimension of V is given to be M, and dimension of W is given to be M. Okay. And notice that the range space was a subspace of our codomain, right? Therefore, the dimension of our range space is less than the dimension of our codomain M. Maybe I can simply plot something like this. So this is V, this is W. So our null space was a subset of null space of A. Okay, was a subset of V. So dimension of the null space is less than the dimension of V itself, and the range space was a subset of range space of R. Was a subset of our codomain. Okay, and that is the linear transformation A. Let's say. So their dimension can be at most M and at most N, right? So dimension of V is equal to N, and dimension of W is equal to M. Then the dimension of their subsets can be at most N or at most M. All right, and the theorem states that the dimension of the range space of that linear transformation plus the dimension of the null space of that linear transformation for any given linear transformation actually is equal to the dimension of the domain. Okay, so this is the domain. And this is called the rank nullity theorem. So we will try to prove that. Okay. So we'll begin by constructing the basis for the null space of A. Okay, so suppose the dimension of the null space of A is less than n, let's say k, then that means that there are k vectors in a basis function for that null space of A. Okay, so I will start by writing let v1 and vk be a basis for null space of A. All right, and notice that k is less than or equal to n. Then the next step is that, so since I'm looking for the dimension of V over here, so maybe I can go a little bit down there. Sorry. Okay. I can complete these bases to be to be a basis for the domain itself. Okay. So we can, let's say, complete this basis to another basis that spans entire domain, okay, domain V, okay. So let's do that, okay. So let's V1 to Vk, sorry, and then I will add those vectors and call them W's this time. Okay, so W1, there will be W2, and there will be Wn minus k. Be a basis for V. So of course, in that basis set, there has to be n elements, right? Because the dimension of the domain is equal to n. And the definition of the dimension was the number of elements in a basis set. So if this is a basis set, I can express any vector v. So let v be a vector in our domain. I can express any vector in terms of a linear combination of these basis set, right? So an arbitrary vector, okay. Vector. Then we can express it as a linear combination. Then we can express V as, so V will be equal to, let's say, alpha 1 times V1 plus alpha 2 times V2 plus alpha k times Vk. And let's say beta 1 times W1 plus beta 2 times W2 and beta n minus k times W n minus k. Okay, so let's have a look at the linear transformation of V. So I would like to see what happens to AV, okay? Then I can apply this linear transformation A to both sides of this equation. So then I can write AV is equal to, let's write down, instead of writing A of alpha 1 V1, since this is a linear transformation, I can write directly alpha 1 AV1 plus alpha 2 AV2 plus alpha k AVK, right? And I can continue as beta 1 AW1 plus beta 2 AW2 and lastly beta n minus k AW n minus k. So this is now a vector W in the range space of A, right? And notice that since V was an arbitrary vector, so W is an arbitrary vector in range space of A as well, right? So I can choose any vector like this. But before that, I would like to ask you what happens to the first k terms in this expression over here. So what is AV1, AV2, and up to here AVK equal to? So notice that these
Zero.
V1 to, exactly, these V1 to Vk were basis for the null space of A. So all of these terms are actually 0, right? So then I can write this, let's say an arbitrary vector W here as a summation I from 1 to n minus k beta I A of Wi. All right, so as you see over here, I'm going towards the claiming that. So if these AW1, AW2, and AWN minus K was linearly independent, then I could claim that that also will form a basis for the vectors in the range space of A, right? Because I was able to write arbitrary vectors W here as a linear combination of them. But I don't know if those vectors AW1, AW2, AW3, etc. are linearly independent or not. Okay. Because I can express any arbitrary vector W in the range space of A as the linear combination of these guys, but we don't know if this is a linearly independent. So let me write the question. Is the set, what was it, AW1, AW2, AWN minus K, a basis for the range space of A, okay? So that's a basis for the range space of A, okay? Maybe we can also write down the conditions for being a basis set. So what are the conditions that needs to be satisfied? So a basis set. So first it should span. It should span range space of A, right? And it should be linearly independent, right? It should be a linearly independent set. Okay. So first of all, maybe we should first clarify this range space of A thing, right? So we said that if we pick any vector, an arbitrary vector in the range space of A, I can express that as a linear combination of these vectors, right? So it looks like these can span the range space of A. But in order to show a span of a set is equal to another vector space, what was the method that we were using? So we should also show a linear combination of these vectors are also in the range space of A, right? And notice that, so if I get a linear combination of these vectors, let's say like a gamma 1 A W1 plus gamma 2 A W2 plus etc. gamma n minus k A W n minus k, that will be simply equal to, I can get the linear transformation out of there, A gamma 1 plus gamma 1 W1 plus gamma 2 W2 plus gamma n minus k Wn minus k as well. So therefore that vector is also, since it can be written as A times another vector, this is in the range space of A as well, okay? So we showed that, and if I pick an arbitrary vector in the range space of A, I can write that thing as a linear combination of these guys. And I said that I picked a arbitrary vector which is written as a linear combination of these vectors, and I showed that that can be written as that can be shown to be in the range space of A. So therefore, it does span A. I think the important thing is that I need to show the linear independence of these vectors. Okay, so these guys over here. So let's check linear independence. Okay, so let's check the linear independence. So what was the condition for linear independence? Huh? Since our quiz was just yesterday, I'm asking those questions more frequently than usual. How do we show a set is linearly independent or not? Or what is the condition that needs to be satisfied there? So
Linear combinations of vectors should be zero, but the coefficients should be also zero.
That should be zero if and only if all coefficients are zero, right? So if I write down, let's say, C1 AW1 plus C2 AW2 plus C n minus k AW n minus k being equal to zero should imply if and only if statement was that all coefficients C1, C2, or Cn minus k is equal to zero. Right. All right, so let's see. So if that new combination is equal to zero, I should show, first of all, if C1s are all zero, then that thing is already zero, right? So it is easy to show. But the other one is that, okay, if that linear combination is equal to zero, can we show all coefficients are equal to zero? So I will scroll down. Okay. So first of all, if I go back to this equation over here, that linear combination being equal to zero, I can get again this A linear transformation out of it, right? So I can write A times C1 W1 plus C2 W2 plus Cn minus k. Sorry, not A. Wn minus k is equal to zero. If that condition is satisfied, this equation is satisfied, right? And notice that if this equation is indeed satisfied, what can we tell about the vector in the parentheses? I apply the linear transformation A and I get the zero vector. Then this has to be in the null space of A, right? By definition. Then if this is in the null space of A, then I can express these vectors in terms of the basis vectors for the null space of A, right? So therefore, then I can express this term as a linear combination of basis vectors for null space of A. So remember that we specified the basis set for the null space of A over here, V1, V2, Vk over there. Okay. Then so let me write it down more explicitly. Okay. Then I can write C1 W1 plus C2 W2 and Cn minus k Wn minus k as a linear combination of V1, V2 up to Vk, right? So let's say some coefficient D1 V1 plus D2 V2 plus dk Vk. Good. So if this equation is satisfied, then I can take everything on the right hand side to the left hand side over here and write down C1 W1 plus C2 W2 plus Cn minus k Wn minus k minus D1 V1 minus D2 V2 and minus dk, sorry, dk equals to 0. So now that's a good expression because of the fact that now I do have a linear combination of these vectors. Let's have a look at those vectors. So I have here v1 to vk, and I have here w1 to wn minus k. Okay, so I will have the v1 to vk and w1 to wn minus k vectors, a linear combination of these vectors. And that is equal to 0. So notice that these vectors are actually, we said that let's v1 to vk and w1 to wn minus k be a basis set for v, right? So it is this set over here. So if I go down, then I said that, okay, so this is a basis set for v. So write it down more explicitly saying that. So this is the basis set for v, right? And if a linear combination of these vectors is equal to 0, then all of these coefficients are equal to 0. Why? Because the vectors in a basis set has to be linearly independent, right? So this is a linearly independent set. This is a linearly independent set. Okay. So if that a linear combination of these vectors is equal to 0, then all of these coefficients c1, c2, cn minus k, d1, d2, dk all have to be equal to 0. Okay. And we show that if a linear combination of these vectors over here is equal to 0, then we showed this all c1 to cn k all has to be equal to 0 as well. And by doing so, we show that this set is also a linearly independent set. So maybe I can write down more explicitly, therefore AW1, AW2, and AWN minus K is also linearly independent. It also spans range, so it's also spans range space of A. Then this is a basis for range space of A. So far so good. Is that, do you have any questions? Because we are almost done.
Hocam burada span'dan bahsederken hani bir şey kontrol ettik ya, o yeterli değil aslında değil mi? Sadece ona bakmak.
İki şeye birden bakmak gerekiyor. So once if you pick any vector in the range space of A, that should be in the second set. And if you pick any element in the second set, that should be in the range space of A. We check both of them actually. Because we said that any vector in the range space here can be expressed as a linear combination of these guys. And we also said that any linear combination here is also in the range space of A. Okay. So if I call this vector, let's say Z for the time being, okay? Let's say Z, that is, okay? We said that, we show that range space of A is a subset of Z, so span Z, and span Z is a subset of range space of A. And from there, we said that range space of A is equal to span Z. we show both of them here. Right? So, and then if we write down the final statement of the theorem. So, okay, we found this Z set, a basis set for the range space of A. Okay, and how many vectors are there? N minus k, right? So the dimension of the range space of A is equal to, then there are only n minus k vectors here. It is n minus k. And what was the dimension of the null space of A? That was equal to, remember, only v1 to vk was the basis vector, so the dimension of the null space we specified as k, and from there dimension of the null space of linear transformation plus dimension of its range space is equal to dimension of their domain, which is n. So, any questions? So that completes our proof of the rank nullity theorem.
Hocam şurada W için hani elemanıdır range space dedik ya. Tam okuyamıyorum da o range space değil mi?
Şurası mı?
Hı hı.
Evet, hani A çarpı V şeklinde yazmışız ya, A of V şeklinde yazmışız ya. Demek ki o range space of A'da yani. Zaten tanımı oydu, hani A, V şeklinde yazılabilen her şey range space of A'daydı. Any other questions? Okay, so in the next lecture, we will solve some examples about how to find range space of linear transformation, null space of linear transformations, and by using their matrix representations. And we will also solve some examples maybe on the change of basis, maybe. And then in the next lecture, we will continue our new chapter about the direct sum, which will end up with us driving the projection theorem, which is one of the fundamental theorems that we will learn in our course. If you don't have any questions, so we can continue in our next lecture then, right? So thank you very much.